Okay, we are now going to turn our attention to acid-base chemistry. And specifically in this set of notes, we're going to be focusing on what's called a proton transfer. Understanding acid-base chemistry is really our first foray into the world of organic reactions. Now first, a large number of organic reactions involve proton transfers at some point, which is one reason why we need to become comfortable with them. However, beyond that, a lot of the ideas that we're going to be looking at in this section of notes to understand acid-base chemistry also have application to other types of reactions. So once again, we're still in that initial part of the course where we're building a foundation so we can better understand organic reactions later on. So let's start by looking at definitions that you learned in general chemistry for acids and bases. So starting with the Arrhenius definition, the Arrhenius definition of acids and bases involves their behavior in water, whether or not they produce hydronium or hydroxide ions. We are not going to be using that definition, so we can move on from that. Okay, the next definition, which is the one that you're probably the most familiar with and what we're going to be using the most, is the Bronsted definition. So just to remind you, a Bronsted acid is a proton donor, and a Bronsted base is a proton acceptor. So let's make sure that we are on the same page with all of this. First of all, a hydrogen with an electron is a hydrogen atom. So this is a hydrogen atom. However, once it's lost that electron, it becomes a proton. Now to push a little bit more on the Bronsted definitions, if you're a proton donor, you must have a hydrogen. And if you're a proton acceptor, what must you have? Well, when a Bronsted base accepts a proton, what that means is that it is forming a bond to the proton. So the base, actually let's be very specific, the Bronsted base accepts a proton by forming a bond to it. So it forms a bond to the proton and pulls it away from the acid. So in that sense, the term acceptor is maybe not the best term, and maybe a proton grabber is a better way of thinking about this because it's the base that initiates the removal of the proton from the acid. So in order to accept a proton, in this context, you have to have available electrons. So a Bronsted base has to have an available electron pair that it can use to form the bond to the proton, because the proton is not bringing any electrons to the party. Okay, now let's briefly look at the Lewis definitions. So a Lewis acid is an electron pair acceptor. So what must you be to be an electron pair acceptor? What must you have? What structural feature must you have to be able to accept a pair of electrons? You have to have an empty orbital because electrons occupy orbitals. So to be a Lewis acid, you have to have an available empty orbital. A Lewis base is an electron pair donor. And so clearly, you must have, if you're going to be a Lewis base, you must have an electron pair. Now the terms Lewis acid and Lewis base and electrophile and nucleophile, sometimes people use interchangeably. So they'll call something a nucleophile or a Lewis base, or they'll call something an electrophile or a Lewis acid. Technically, there is a distinction between an electrophile and a Lewis acid, but it's not important for what we're doing here. So we're not going to worry about that, but what we are going to do is review the definitions and the ideas surrounding electrophiles and nucleophiles because we're going to be using them so much in the course. So remember that an electrophile is something that seeks electron density. So it's seeking or accepting electron density. And so if it's going to accept electron density, it will have to have an empty orbital to accept that density into. And like we mentioned previously, it will often have partial positive charge or positive charge. Sometimes people abbreviate electrophile E+, so you'll see me using that abbreviation. Nucleophiles are abbreviated either NU or NUC. Now remember that a nucleophile has electron density to share. And it often has partial negative or negative charge associated with it. Now the electron density that it has to share could be in the form of a lone pair, or a pi bond. So those are the two most common examples that you'll see. Okay, so with the definitions in hand, what we're going to do now is focus for the rest of the packet on the Bronsted-Lowry acid-base reaction, which is nothing more and nothing less than a proton transfer. So a Bronsted-Lowry acid-base reaction is just a proton transfer. The reaction, as you know from Gen Chem, involves two conjugate acid-base pairs. So in a proton transfer, the proton is transferred from the acid to the base. If this is occurring between two different chemicals, then you should know that this is the fastest reaction that you're going to see in organic chemistry between two different chemicals. So these proton transfers are the fastest reaction between two separate molecules. Protons are light, readily transferred, assuming that the acid is strong enough to give up the proton. Protons are light, and so the rates for these reactions are very, very fast. Okay, so let's write out a sort of a general example of one of these reactions, just so we can remember who all the players are and what labels we can put on them. Okay, so we have B with a lone pair plus HA going to BH plus and A minus. In this example, B is the Bronsted base. And it's related to what we call its conjugate acid. So BH plus is the conjugate acid. And notice that it differs from B by just one proton. The same is true for HA and its conjugate base. So HA is a Bronsted acid, and its conjugate base is A minus. So again, the base accepts the proton by forming a bond to it. When we looked at frontier orbitals in the previous packet, we looked at some chemical mechanisms so that we could determine what was going on in the reaction and which orbitals were involved. So now we're going to look at the mechanism of proton transfer so that we know how to draw that. We're going to use, to start out with, water. And we'll just keep the acid general at this point. We'll call it HA. In this example, HA is the Bronsted acid, and water is going to function as the Bronsted base. The base accepts the proton from the acid, so the base is supplying the electrons in order for that to happen. That means that the first arrow that we draw is going to start at the base. Just like you saw in the previous examples of frontier orbitals, where arrows originated at nucleophiles that were attacking, that is to say, forming bonds with electrophiles. So the base uses one of the lone pairs on the oxygen to accept the proton in the acid. So we would draw the arrow like that. So the arrow originates at the lone pair and points right next to the hydrogen. That means that the oxygen is forming a bond to the hydrogen. The hydrogen can't be bonded to the oxygen and to whatever A is, which means that the bond between H and A has to break, and it's going to break towards A. So we start an arrow at that bond, the HA bond, and we point to A. Okay, now this is very important. This bond right here that I just highlighted in blue, you have to draw that bond if you're removing the proton, because you have to start an arrow at that bond, not just somewhere on the page. So that bond must be explicitly drawn in when you're drawing the mechanism of a proton transfer. Okay, the result of this is that now water has acquired a new proton. So now it's H3O+, known to the fans as the hydronium ion. This is the conjugate acid. The pair of electrons that I highlighted in blue in the HA bond have moved on to A. So now A has control over both those electrons, which means it develops a negative charge. A is the conjugate base of the acid we started with. Now let's repeat this exercise, only we're going to use an actual acid instead of a generic acid, HA. We'll use water again. And what we're going to do is replicate a reaction that you probably talked about a number of times in Gen Chem. And that is the dissociation of a weak acid in water. So this is what's going on when you put a weak acid like acetic acid, which is the structure I just drew, into water. It's this blue proton that's the most acidic proton in acetic acid. So that's the one that the water is going to pull off. So just like the example above, use either of the lone pairs in the water, start an arrow at the lone pair, point to the hydrogen, and then start a second arrow at the OH bond and point to the oxygen, which is where the electrons in that bond are going to end up. Once again, we get hydronium ion. And now we have an actual conjugate base. And that is this guy, which is the acetate ion, which we met when we talked about resonance. So this is our conjugate base. Remember, this is what's called a carboxylate. So the conjugate base of a carboxylic acid is a carboxylate. Hydronium is the conjugate acid. And then in this example, water, again, was the Bronsted base. Acetic acid, the Bronsted acid. The bottom of this page is printed an admonition that's very, very important. And that is that the arrow always starts at the base and points to the proton in the acid. It's never the other way around. So you would never, ever start an arrow at a proton and point to where that proton is going, because the electrons are showing the movement, the arrows are showing the movement of electrons, not protons. So these curved arrows show the movement of electrons, never protons. Okay, let's take a little dip into some quantitative stuff. So I'd like to remind you of a few parameters that you saw in general chemistry, and those are Ka and by extension pKa. So let's start by thinking about the reaction of a weak acid we'll call HA in water. So that's pretty much what we've been doing in the previous couple of examples. And so we know that HA, when we place it into water, is going to dissociate partially because it's a weak acid to give us hydronium ion and the conjugate base of HA. We can write an equilibrium expression for this. So following the format of concentrations of products over concentrations of reactants, with each of those concentrations raised to the power of their stoichiometric coefficient. Now, the stoichiometric coefficients in this reaction are all 1, so we don't have to worry about that. But we can set up an expression as follows. We're using concentrations, so we're going to call this a Kc. So Kc is the concentrations of the products, so hydronium ion, times conjugate base concentration, over the concentrations of the reactants, so HA, times concentration of H2O. But what you may remember is that because water is a pure solvent, and because its concentration is so large to begin with that it's not changing very much, that what we're going to do is multiply both sides of the equation by the concentration of water. So those terms cancel on the right side of the equation. And so now what we have is a new equilibrium expression that we call Ka. So specifically the acid dissociation constant. So let's rewrite that down here. So Ka is equal to the H3O plus concentration times the A minus concentration over the concentration of HA. So Ka is a measure of acid strength. How much is an acid dissociating? Or another way of thinking about this is how readily is it donating a proton to a base? So Ka, a measure of acid strength, so how much an acid dissociates well, we can think about this as how readily it donates a proton to a base. Now, if we look at the terms and look at how the equation is set up, then we can make some predictions. So the larger the Ka, so if we have a relatively larger value of Ka, what that means is that we're going to have more in the numerator. So the concentrations in the numerator are going to be higher than the concentrations in the denominator. So we have more stuff in the numerator, which means more product. So a larger Ka means that you have more dissociation, or more proton donation, and so that is a stronger acid. So hopefully all of this is ringing some bells from general chemistry. A smaller Ka, relatively speaking, on the other hand, means that the term in the denominator is larger, meaning you have more reactants than you do products. So the reaction hasn't gone very far to the right side, to the product side. So that refers to less dissociation, or a weaker acid. You'll probably remember that where we ended up when we talked about Ka in general chemistry was pKa, because pKa is just a more convenient way to express Ka. Kas are going to be numbers that typically we express in scientific notation. For example, with acetic acid, Ka is 1.8 times 10 to the minus 5. The pKa, though, is going to be a small, readily reportable number. In the case of acetic acid, the pKa is 4.8. So that's much easier to work with and to relate to others. So you probably remember this equation. The pKa is equal to the negative logarithm of Ka. And so because of the logarithmic scale and that negative sign, Ka and pKa have an inverse relationship. So what we mean by that is the larger the Ka, the smaller the pKa, and both of those correspond to stronger acid, whereas a smaller value of Ka, again this is all in relative terms, corresponds to a larger pKa value, which signifies a weaker acid. Let's think a little bit more about these acid-base reactions, and specifically about equilibrium. Okay, so let's think about that reaction of water and acetic acid. So we drew a mechanism for that, but what we're going to do now is write this out as an equation in the fashion that you saw in general chemistry. So water and acetic acid are in equilibrium with H3O plus and the acetate ion. So labeling everything, the water is accepting the proton from the acetic acid, so it's the Bronsted base. Acetic acid is the Bronsted acid. Hydronium ion is the conjugate acid of the base. And acetate ion is the conjugate base of the acid. So right away, notice one thing, and that is that we have two conjugate acid-base pairs. That's going to be true for every single Bronsted-Lowry acid-base reaction. Two conjugate acid-base pairs. That's important enough to write down. Every proton transfer involves two conjugate acid-base pairs. Which means that you have two acids in the reaction and two bases in the reaction. On each side, there's an acid and a base, just like we see in this picture. Okay. So, how do we know which side of this is favored at equilibrium? And that's a question that's printed down below in these notes. So which side of the reaction is favored at equilibrium? Now the first thing we need to do is try to figure out what that means. What does it mean for one side of a reaction to be favored over another? Well, what this means simply is that you have more stuff on that side. So the favored side is going to be the side with the higher concentrations. So the higher concentrations of chemicals, let's say. Okay, so now we know that. So how do we tell? How do we know, looking at this equation, which side will be favored? We can do that very, very easily if we have pKa values. So let me give you some pKa values. What we need are the pKa values for the two acids involved in the reaction. Now, as an aside, some of you might be thinking back to general chemistry and thinking, well, you know, when we start with Ka, it's just a quick step to pKa, and then after that, it's really easy to get to Kb and pKb. The good news is we don't need pKb and we don't need Kb. All of the information that we would get from those is embedded in pKa. So we're really just going to be using pKa values and not even that many of them. We will memorize, or you'll memorize, a small handful of them for this semester, a few more next semester, but really, you don't have to memorize that much in terms of those pKa values. So let's apply some pKa values here. So first of all, the pKa of acetic acid, as I mentioned previously, is 4.8. So let's put that number in there. And the pKa of the other acid involved in the reaction, the hydronium ion, is negative 1.7. So So negative 1.7 is the pK for the hydronium ion. Now this brings up a point. First of all, you're used to dealing with things that all fall within, that have values of pKa's and so on, that fall within the pH scale that you're accustomed to, which is 0 to 14. What you're going to see in organic chemistry is that you'll have pKa values that fall well outside that range. And hydronium ion is an example of that. So something that has a negative pKa is by definition a strong acid. Everything else would be considered a weak acid. But we'll get into that a little bit later. So I just wanted to give you a heads up on that the numbers might be a little bit outside the scales that you're used to dealing with. So in organic chemistry, almost anything can function either as an acid or a base, depending on what it's around. It's just how likely is that to happen, and that's where the pKa values come in. All right, so let's look at these two. Now, what do these numbers tell us? Well, first of all, we know that the smaller the pKa value, the stronger the acid. So right away, we can assess the fact that the hydronium ion is a stronger acid than the acetate ion. So that's step one. We know which is the stronger and which is the weaker acid by virtue of their pKa's. Now, another thing that we can get from this is the fact that the weaker acid in one of these proton transfer reactions, the weaker acid is always going to be on the same side of the equation as the weaker base. Remember, just like we have two acids, we also have two bases. So the weaker acid will always be together on the same side of the equation with the weaker base, and the stronger acid is always going to be on the same side of the equation with the stronger base. Okay, so what we know right away, without looking up any numbers or KBs or what have you, is that the acetate ion is a stronger base than water. Okay, so let's make a note of that. The weaker acid and weaker base as well as the stronger acid and stronger base are always together on the same side of the equation. Now, whether that's reactants or products, that's going to vary depending on the acids and bases that you have that you're working with. Okay? But they're always, the weaker ones are always on one side, the stronger ones are always on the other. All right, now to go back to our question, which side is favored? Okay, for this, we're going to need to understand what's meant by a stronger acid versus a weaker acid. So a stronger acid is more likely to dissociate. It's more likely to donate a proton to a base. So a stronger acid is more likely than a weak one to donate a proton to a base. So what that means is that in this example, if you're on the right side of the equation, the hydronium ion is much more reactive than acetic acid. So it's going to react. That's going to send you back to the left side of the equation. Okay? Where you get to acetic acid and water, those are weaker, so those are less likely to react. So what happens is that things, in this example, things are going to pile up on the left side of the equation. So that would be the side that's favored. So the side that's favored in a proton transfer is the side with the weaker acid and weaker base, because those are less likely to react. When they would react, it would push you to the other side of the equation. So the side that's favored in a proton transfer is the side with the weaker acid and weaker base. Okay, so we did all of that just to answer that one question. Now, going forward, all we need to do is look at the pKa values, compare the pKa values, and then we're done. Okay, the one that has the higher pKa, the acid with the higher pKa, that's going to be on the side that's favored in the reaction. Now, one of the numbers that came up in this discussion is this one right here, which is the pKa of acetic acid, which is a carboxylic acid. That is a number that you should remember, okay, but not that number specifically. So I'm going to make a little list down here. So the pKa's to know so far, I'd like you to know that carboxylic acids have pKa values between 4 and 5, typically speaking. So this is something to memorize. So that's going to be one of 4 or 5 pKa's that you'll need to memorize before we're done with this packet.